let's start with this imagination of a tug of war. On one hand, you have the nucleus trying to pull the electrons, and on the other hand, the electrons themselves are trying to stay as far away from each other as possible. You get it? The nucleus pulling the electrons trying to be away from each other. Every single property that we're going to discuss today are all going to link back to the exact same idea of how well the nucleus can pull the electrons towards itself and to what extent are electrons pushing themselves away from each other. So whatever we are discussing today, atomic radius, ionization energy, electron affinity or electron gain enthalpy. In some books they write it like this. And even electronegativity. We're going to discuss all of this, and you'll see that all of this is going to relate back to this exact topic of linking of how well the nucleus is pulling electrons and how they end up staying away from each other. They're just different ways of measuring who's technically winning this tug of war. So once we understand how much a nucleus tends to pull an electron as we increase the atomic number, these trends will be extremely easy to memorize. Or rather, keep in mind, you don't have to technically memorize them at that point. You'll be able to derive every one of them on that spot. In today's session, we'll be building this exact understanding. Before we touch on to any property, let us discuss nuclear charge and something called as the shielding effect. So nuclear charge is of course the number of protons. Each proton has a specific charge that it possesses. So the more number of protons, the more the electrons are going to be pulled towards the nucleus. That's logical. But electrons themselves, say if I have a nucleus like this and I have an electron cloud like this, I have another electron cloud like this. If I want to measure, say, one electron over here, if I want there to be an attractive force like this, don't you think this electron cloud over here is going to create some issues? It's going to create a negative charged region. So when an electron is being pulled towards the nucleus over here, it is going to start getting repelled over here. That itself is what we end up calling the shielding effect, where inertial electrons are going to act as this buffer between an electron being pulled towards the nucleus. So everything that we will be talking about deals with this effective nuclear charge, which is nothing but the calculated nuclear charge, number of protons, minus this sigma value, which we call the shielding constant. Again, we're dealing with the effective nuclear charge, which is nothing but the nuclear charge overall minus the shielding constant. So when you look at a periodic table and you want to move across a period, what you can notice is that across a period, I will abbreviate across a period as this. Across a period, the Z value increases, but so do the number of electrons. So now if I want to look at this, if I have electrons being added in the same shell, this value does not change, but this value is. So Z effective increases across a period. Very important to know. Now if you go down the group, sure, this is increasing, but my number of shells also increases, meaning my shielding effect का constant increases, thus the Z effective decreases. So that is our interesting idea of what happens across the period and down the group. And this is what we are going to look when we look at how this manifests into a variety of different properties. So let's start off our discussion with atomic radius. Your atomic radius is kind of interesting to measure. If I draw a nucleus and I draw an electron cloud, this is still a probability density. Like, you can tell that an electron can exist within this region, but how do you know where to draw the boundary? Last time we discussed, like, the probability range is somewhat like this. But how do you measure this? This is still a theoretical way of doing this. How do we measure this? So the idea then arises of measuring them depending upon the kind of bonds they form. So you can technically measure a covalent radius. You take two atoms, consider them as spheres, look at the molecular distance, look at the bond length, divide it in half, you get your covalent radius. You can also think about a metallic radius, where it will just be you looking at two metal cores. They'll of course be close by, and you take the distance accordingly. That's how you do it. If you have an ionic solid, you just measure the distance between your lattice points. So these are the different ways of measuring atomic radii, but the trend remains consistent. For my atomic radius to decrease, my effective nuclear charge has to increase. For atomic radius to decrease, my effective nuclear charge needs to increase. Why? If my effective nuclear charge is increasing, I'm pulling electrons closer to the nucleus, thus I'm shrinking the atom. So now where do you think it's going to be possible to increase the effective nuclear charge? It's going to be across a period. So when you go across a period, the atomic radius decreases because the number of protons increases, the electrons are in the same shell, thus they're pulled closer. There are certain caveats over here as well. Now, what are these caveats going to be like? When you look at shells which are half filled or fully filled, there is a slight extent of repulsion. Let's look at the example of beryllium. 1s2, 2s2, right? Your electrons are full in both of these shells. Thus, when you measure the atomic radii, you will see that there is not as sharp of a decrease over here as you will see within your other elements within the same period. The same thing can be argued for nitrogen, where you have a p orbital filled like this. And you will see a lot of anomalous properties when you consider that as well. That's for another class for our discussion. The very extremely important exception to this is of course your noble gases, because if you compare them to their respective halogens, their atomic radii are extremely large. Partly that's due to the extreme electronic repulsion because of their fully filled orbitals. Plus we measure their atomic radii slightly differently because they usually don't form compounds. It's only down the groups, xenon, all of those ones that form compounds, and that too very rarely. So we end up measuring something called as the van der Waals radius. And that, as I said, it's measured significantly differently, so it's not as useful for us to compare. So that's there. Say if I want to take a metal, let's take an example, sodium, and I want to chuck up an electron. The energy that is required for this is what I call the ionization enthalpy. Since I'm taking out only one electron, I call it the first ionization enthalpy. The energy required to remove the outermost electron from a metal or an ion. Now, for most cases, this is going to be an endothermic reaction because nuclei don't really like to lose stability. The trends that we will be discussing is which one of them are least endothermic and which are most endothermic. That's how we look at these things. What happens across a period? Normally, ionization enthalpy generally it increases. Now, the caveat here is when I say it generally increases, because here is where you have those interesting exceptions of your half-filled and fully filled orbitals. Before that, let me come into why it generally increases. Your Z effective increases across a period, meaning electrons are pulled closer, meaning it takes more energy for us to remove an electron. Logical. With exceptions of half-filled and fully filled orbitals, you obtain stability. To remove electrons from these particular orbitals, it is even more difficult. So you will obtain slight, the increase in ionization enthalpy becomes a little sharper. And in cases where, say you have a, sure, you know what? If you have a 2p4 system, if you have a 2p4 system, or you have a scenario where you like have 2p6, 3s2, or 3s1, my bad. Something where if I chuck up an electron, I reach a stable state. There the ionization enthalpy ever so slightly decreases because it's much more feasible or it's much more stable that way. So that's very interesting for us. Now a couple of more observations that are made. There is a dip when you go from magnesium to aluminum because of the introduction of d orbitals and the shielding effect that they possess. And even then, when you look at, say, sulfur to phosphorus, sulfur has paired electrons. So electron and electron repulsions allow for sulfur to remove an electron easier. Phosphorus has 3 unpaired electrons, something like this. That's why its ionization enthalpy is higher than it's for sulfur. So that's where our discussion for ionization enthalpy ends for this particular lecture. Now we move to electron gain enthalpy or electron affinity. What do we measure over here? Say if I have chlorine like this and it accepts an electron, the energy corresponding to this will be the electron gain enthalpy, and it tends to be exothermic. So we try and measure how negative the electron gain enthalpy will be when we go across a period and down the group. So across the period, what happens? This increases, meaning the nucleus is bound to pull more electrons. So if I add an electron, it becomes much easier for this to be more and more exothermic. So this becomes more negative across a period. Down the group, what happens? This decreases. So your electron gain enthalpy becomes less negative. That's our idea over here. Again, certain exceptions. Noble gases have no electron gain enthalpy because it is not at all feasible for it to gain another electron. Nitrogen is stable. Adding an electron will disrupt its stability. Its electron gain enthalpy is less negative. Whereas oxygen's electron gain enthalpy is more negative because for it to gain electrons, it's much more feasible. Same when you compare fluorine and chlorine. If I add another electron in fluorine, fluorine being extremely small causes repulsions. So its electron gain enthalpy actually is less negative in comparison to chlorine, which is slightly bigger. So when it accommodates an electron, it's much more feasible for it to do so. That's the thing we're keeping in mind. Moving on to electronegativity. So electronegativity, I'll preface this by saying that it is a relative measurement. You cannot measure electronegativity independently. So when I tell you that fluorine is the most electronegative element, it is in comparison to all other elements. So when I create bonds, when I create compounds, the electron density tends to shift towards fluorine in almost all cases. Thus, it tends to be the most electronegative element. So that's the idea of where we end up having a relative measurement. So this relative measurement of electronegativity is plotted using a Pauling scale. You'll see it on the screen soon. Where fluorine happens to have a value of 4 and then it decreases further and further. And this is again in comparison. It is in relativity. This is not an independent measurement. But we can still talk about trends. So across the period, what happens? Same thing, Z effective increases, meaning electrons will be like there's a tendency when comparing one element of this period to the previous element that this element will tend to pull electrons closer. So electronegativity tends to increase. Down the group, this decreases. We obtain a decrease with electron negativity as well. So simple thing with electronegativity, the smaller the atom, the more electronegative, the more it has, the more nuclear charge it possesses, the more electronegative as well. So now, keeping all of this in mind, let's maybe solve some questions. I would want you to answer the order of increasing atomic radius for sodium, magnesium, potassium and aluminum. Your options are if you can access the quiz feature, I would want you to answer there, or else you can answer in the comments down below too. The increasing order of atomic radius. Okay, now let's arrange certain elements in the order of their increasing electronegativity. So for electronegativity, I would want us to arrange nitrogen, oxygen, fluorine and chlorine, okay? Your options are, of course, my bad. Arrange this in the increasing order of electronegativity. Again, if you can access in the quiz feature, you may answer there or else comment down below. So to summarize all of this single idea of how I am pulling electrons versus how electrons are pushing themselves away, that is what gives us an idea of all of these different periodic trends and how they move about in a period, across a period more appropriately, and down the groove. All of them come down to the idea of effective nuclear charge. If you have a higher effective nuclear charge, a smaller radius, higher ionization enthalpy, more negative electron gain enthalpy, so on and so forth. You add more shells, Z effective is going to decrease and these trends flip. From the next class onwards, you're going to start applying this idea into individual blocks. So S block, P block, D block and F block. That's how you're going to be taking up all of these trends and understanding their physical and chemical significances with each of these elements. So I will see you there.